The ideas of linear independence and span are very closely related. Let's take a look at a particular collection of vectors. These are generic vectors, but if I want to look at the span of this set of vectors, then I'm looking at the complete collection of all possible linear combinations of these vectors. Okay, but let's take another vector. Let's say u. And let's say that we find out that u can be written as a linear combination, I think I'll use different letters here, a linear combination of, I don't know, v sub I and v sub j. Well, since the span of the set of vectors v is all possible linear combinations of the vectors in the set v, then since u is a linear combination of the vectors in V, U must be in the span of V. Or we could say that U is in the subspace spanned by V. I heard another video presenter recently say or describe a subspace as a subset where you can do linear algebra. A subspace of a vector space is a subset of the vector space where you can do linear algebra. I really like that description. Remember that a subspace is just a subset of the space, a subset of the vector space, where the zero vector is included, scalar multiplication is defined, the space is closed under scalar multiplication, and vector addition is defined. So the space is closed under vector addition. So the subspace, or a subspace, is just a subset where it's possible to perform linear algebra. So we can either say then that the vector u is in the span of the set of vectors v, or it's in the subspace spanned by the vectors in the set of vectors v. If it turns out that u is one of the vectors in this set of vectors, in other words, if I renamed this, say, for example, v sub k, and that by implication then that vector is in here, then I can say that this vector v sub k is in the span of this set of vectors, but it's also in that set of vectors. And that means that v sub k, which is a linear combination of these vectors, is in this set of vectors. And that means that this set of vectors is linearly dependent. So I can say this: a set of vectors, like this one here, is linearly dependent if at least one of the vectors in that set is in the span, it's a linear combination, is in the span of the other vectors in the set. Not only that, but I can say the reverse. I can say that if a vector is in the span, if a vector I know is in this vector space, if a vector is in the span of the other vectors, then that automatically means that this, because it's a linear combination, that this set of vectors is linearly dependent. And so I would write that as two separate statements. One, a set of vectors V is linearly dependent, and the other one is that at least one vector, and we're calling it V sub k, which is an element of the set of vectors V, at least one vector V sub k and V is in the span of the other vectors in V. And because one of these, this first statement implies the second statement, but also the second statement implies the first statement, I can write if and only if. That very specific mathematical phrase means that this is true in both directions. If I know a set of vectors is linearly dependent, then I must be able to find at least one vector that's in the span of the others. Or if I am given a vector that I know is a linear combination of other vectors in the set, then it's automatically true that the set of vectors that I'm looking at is linearly dependent. Instead of the words if and only if, occasionally you will see this funky looking symbol, IFF, that's just shorthand for if and only if. It means exactly the same thing. It's just mathematicians are notoriously lazy. This is one way to write that same thing. And another way is to take kind of a double arrow and put heads on both sides of the arrow. So here what I'm saying is the implication goes in both directions. You might see any one of those symbols in the statement of a theorem. They all mean exactly the same thing. Now, since this vector is already in the span of these other vectors, the implication here is that I and j, vectors vi and vj, are in this collection of vectors, in this set. V sub k is also in this set, is itself a linear combination. So V sub k is in this set, but it's already a linear combination, so it's somewhat redundant in terms of the span. So if I take V sub k out, then I have a much smaller set here to work with, well, smaller by 1. And if there are other such vectors, let's say I have V sub m is equal to C sub 3, V sub p. I'm just picking letters randomly here now, and C sub 4 times V sub, oops, I wrote a C there, V sub q. Now, mathematically speaking, alphabetically speaking, P and Q come after N, but I'm implying by my use of the V vector here with subscripts that all of these vectors are in this vector space, okay? If V sub m turns out to be another vector in here that's a linear combination of the other vectors, I could add a third one here, plus C sub 5, V sub s, for example. Doesn't have to be just 2, could just be 1. If I find other vectors in the set of vectors that I'm working with that are already linear combinations of the other, then I can remove them without changing the span, because the span is linear combinations. In other words, if I take V sub m out of here, I'm not removing V sub m from here. I'm only removing it from the set, because I can get V sub m by looking at one of the linear combinations of the remaining vectors. Okay, so let's say that we take out all of the vectors that are already combinations of the other vectors in the set, and we call that the minimal spanning set. Let's say you take vector space V, which was V sub 1 through V sub n, and we'll take out vectors V sub k and V sub m, and I'm going to write here, and all other similar vectors. And then actually, because I'm taking some vectors out of this set, this is no longer the set V. I'm going to call this the set S. It's based on the set V, but it's had some vectors taken out of it, so it's not equal anymore. But what I can say is, because the set S has been made up of all the vectors in set V minus the ones that are linear combinations of the other vectors in set V, the span of S and the span of V are the same. These are equal. This assumes, of course, that we've removed all the vectors in V that are linear combinations of all of the other vectors, or in some of the other vectors in V. It turns out that there's a pretty easy way to determine a minimal spanning set of vectors. So I'll take a look at that on the next slide. It turns out that the minimal spanning set of a vector space is the pivot columns in a matrix. Here are 3 vectors. If I make a column matrix out of these vectors, I'll get something that looks like this: 1, 2, 0, 7, and 2, negative 3. And if I then row reduce this matrix, let's see, I'll take negative 2 times row 1 and add it to row 2. That'll put a 0 in this first position here in row 2. So I'm going to replace row 2 with that. That gives me negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 0 is 0, plus 7 is 7. Negative 2 times 2 is negative 4, plus negative 3 is negative 7. And then I'll scale my second row. And in the result, I can see that both my first and second columns are pivot columns. This is a 1, everything below it is a 0. This is a 1, everything below it is a 0. My third column is not. So what that tells me, first of all, let me make a couple of things clear. I'm going to say the set of vectors v is equal to these three vectors, vector 1, v1, v2, and v3. That's my full set v. And now I can say that a minimal spanning set, I'm cheating and abbreviating that, a minimal spanning set S of V, so my minimal spanning set is called S, that is made up of vectors v sub 1 and v sub 2, because the first and second column in my reduced echelon matrix, reduced echelon form matrix, are pivot columns, but the third column is not. So that is a minimal spanning set of V, but it is not the only one. As it turns out, I'll put this over here, V2 is equal to C1 V1 plus C2 V3. Maybe I'll make this a 3 as well, just to keep it consistent. And I forgot my subscript there. I know this because I built V2 that way. I chose it specifically because it was a linear combination of the other two. What are C1 and C3? Well, remember, we have a way to figure that out as well. I've moved things around here so that my V2 is over on the right-hand side. I have to be careful when I do this because I have to remember that what I'm looking for is the constants here, the scalars or the weights, right? And if I perform elementary row operations on this matrix, I get eventually that C1 is 2 and C2 is -1. So I found V3 by taking, V2. I found V2 by taking 2 times V1 and adding -1 times V3. And really my only point in showing you that is to indicate that in doing this matrix arithmetic here, I have found a minimal spanning set, vectors 1 and 2, right? Vectors 1 and 2, but it's not the only one. Another set can be found, if we call the first one a minimal spanning set, we call that first one S, and we call this other one S prime. Another minimal spanning set of the set of vectors V, V1, V2, V3, is the vectors V1 and V3. So the point is that usually you will need to find a minimal spanning set, but when you do, you should know that it's not necessarily the only one.